Welcome back to AEC course. So today let us look at the working of parallel clipper. So in case of parallel clipper, as you know that the diode is connected right across the load. So first let us consider parallel clipper on the basis of ideal diode analysis, and then we can consider a practical diode analysis. So first let us consider this circuit. This is your AC source, current limiting resistor RS, and then comes the diode, and right across the diode load is connected. Right, so this is what we have defined. Diode is connected across the load, and here is the diode and here is your load. So right across the load we'll be measuring the output voltage. So as you can see that measuring the voltage across the resistor is as good as measuring the voltage across the points A and B. Right, that's because load resistor RL is directly placed across the points A and B, and that's why in most of the standard textbooks you don't find the load resistor. Okay, so what you have to understand is that if there is no load resistor, you have to understand is that right across the load terminal output voltage V0 is extracted. So the simplified circuit looks something like this. A current limiting resistor, and this is your diode, and across the diode what are we measuring? The output voltage. So we have just removed the load resistor RL because right across RL the voltage V0 is measured, just for the simplification purpose. Okay. Alright, so we are under the assumption that ideal diode analysis. So first let us consider ideal diode analysis. So let me redraw the circuit. And for ideal diode analysis, as usual, first we will analyze the circuit for a positive half cycle followed by a negative half cycle. So first let me write, say, positive half cycle. So for the positive half cycle, let us put the polarity for input source Vi, upper side positive, lower side negative, followed by current limiting resistor Rs and the diode, and across the diode we would want the output voltage to be measured. Okay, now in this case, as we are considering the diode is ideal in nature, in short, ideal diode, I have represented as ID. Okay, so as you can see that the positive terminal of the source, right, is connected to anode terminal of the diode through resistor Rs, and similarly the cathode terminal is connected to the negative terminal of the source. So we can say that the diode is forward biased. So for the positive half cycle, diode gets forward biased. When the diode gets forward biased, we can replace the diode with a short circuit equivalent or a closed switch. We can replace it with a closed switch. So this is how the circuit is going to appear. This is Rs, and this was your diode. Now the diode is behaving like a closed switch, and that's why we have closed the contacts here. So between anode and cathode there is a flow of current, and this is where you are observing the output. Right. So as you can see, you are measuring the output across the short-circuited anode and cathode terminals, and we know that in a short circuit voltage is 0. So this is the short-circuited part. So across A and K you can see there's a straight conductor being placed. So this is nothing but a short circuit element. So in a short circuit situation, the output voltage becomes 0. So you can say that the entire positive half cycle is being clipped. And at what level we are going to clip? We are going to clip the input voltage at 0 volt level. So entire positive half cycle of the input is going to get clipped. Alright, fine. So this is the analysis of positive half cycle. Next, let us see the negative half cycle analysis. So you can consider it as part 2. So let's see what will happen during the negative half cycle. Alright, so what are we going to do? During negative half cycle, we are going to flip the polarity of the input. So this is your input Vi, upper side negative, lower side positive, followed by current limiting resistor Rs and the diode. This is your anode terminal and this is your cathode terminal. The output voltage will be measured across the diode terminals. Okay, now if you investigate this particular circuit, you would see that the positive terminal of the battery or the source is connected to cathode terminal of the diode. And on the other hand, the negative terminal of the source is connected to anode terminal of the diode through the resistor Rs. So positive terminal of the source is connected to cathode terminal, so we can say that diode is reverse biased. Diode is reverse biased. And the equivalent circuit looks something like this. Series resistor. So diode is reverse biased, so this is as good as diode can be treated as an open switch or open circuit. This was the diode place. So what are we doing? We are going to open the or removing the diode symbol. So that will model an open circuit scenario. You can apply KVL and you can determine the output voltage. So you have an open circuit path. Let us apply KVL. Okay, in the anti-clockwise direction. I am taking the direction of the source voltage Vi. So minus to plus is Vi. And then we have the polarity for the output, which is minus to plus. So this becomes plus V0 is equal to 0, or V0 is equal to minus Vi. So over here you have to observe this sign minus Vi. So what do we mean by this minus sign? So minus sign simply indicates that the signal is inverted. Okay, and why the signal is inverted? Because we have considered the negative half cycle. So your output is nothing but negative half cycle of the input. Negative half cycle of the input. Okay. So just to summarize, during positive half cycle, our output was at 0 volt level. That means to say the voltage is being clipped. And on the other hand, this is during positive half cycle. And during negative half cycle, we obtained output voltage is equal to minus Vi. Minus Vi is nothing but the negative half cycle of the. Let us draw the waveforms. So first let us sketch the input waveform Vi, and right below Vi you can plot the output waveform V0. So input is a sinusoidal. Okay, the maximum value is Vm, and the maximum value in the negative direction is minus Vm. Alright, and Now let us look at the analysis of positive half cycle. So during positive half cycle of the input, the diode was short circuited, and due to which we obtained output voltage as 0 volt. So for the entire positive half cycle of the input, output stays at 0 volt level. Alright. And during negative half cycle, we have obtained the output voltage as minus Vi. That means to say the output is nothing but replica of the negative half cycle of the input. So this is your waveform. So as you can clearly observe that in this particular circuit, what is getting clipped? We are clipping the positive half cycle. So positive half cycle is clipped. And that's why you can call this particular parallel clipping circuit as parallel positive, because it clips or shapes the positive half of the input signal. Alright. So now let us plot the transfer characteristics. 4 quadrant, positive input, negative input. Okay, negative input stands for negative half cycle. Similarly, positive output stands for positive half cycle, and minus V0 stands for negative half cycle. Okay, so first let us look at the positive half cycle operation. So in the positive half cycle, what did we get? We got output is equal to 0 volt. That means to say, whatever may be the magnitude of the input, your output always stays at 0 volt level. That means to say entire positive half cycle is clipped. On the other hand, if we visit the negative half cycle of the input, we are going to get the output is equal to the replica of the negative half cycle of the input. So for the entire negative half cycle, this is the upper limit for the input or the output. It's a complete AC signal you are going to get in the output, and that's why transfer characteristic is nothing but a straight line with a slope of 1. So slope is 1, angle is 45, and slope is 1. So this is your transfer characteristic. Okay, now let us look at practical diode analysis. Let us see how the practical diode will reshape. Let me write B. So in case of practical diode, what we do is we consider Vk. So Vk is considered. Vk is considered. So whenever the diode is going to get forward bias, we are going to replace the diode symbol with DC source having a potential of Vk. So let us consider the same circuit, that is positive parallel clipper. Since we are considering a practical diode, so what we will do, we will bring in the Vk into the picture. So what we can do is we can consider an ideal diode in series with a DC source with a potential of Vk. And note that the Vk is being placed in such a way that the Vk always opposes the diode conduction. That means to say the property of barrier potential is to keep the diode in reverse biasing mode, and that's what it does. So that's why the cathode terminal of the diode is connected to positive terminal of Vk, because Vk keeps the diode in reverse biasing mode. And this is where we are going to observe the output. And now you can consider the positive half cycle. So let's see what will happen during positive half cycle. So during positive half cycle, the upper side of the source attains positive polarity and the lower side of the source attains negative polarity. And you can clearly observe that in this particular circuit there are two sources. On one side you have an AC source and on the other side you have a DC source. So you have to bring in the source comparison into the picture. So the AC source tries to circulate the current in the clockwise direction. We can write IAC. On the other hand, the DC source is trying to circulate the current in the anti-clockwise direction. That means to say in the opposite direction. So that can be considered as IDC. Both the sources are opposing each other, and that's why during positive half cycle the source comparison comes into picture. Now the question is, which source is able to drive the circuit? Okay, so for that let us consider the two scenarios. Scenario 1 going to be the instant at which your input source is less than Vk. That means to say the potential of input is less than the potential of barrier potential. Remember one thing, this barrier potential is analogous to DC source, which is having fixed voltage, 0.7 for silicon, 0.3 for germanium. On the other hand, this Vi is an AC source, and in case of AC source, potential is not fixed, right? Because AC source can have infinite instantaneous values. So you are comparing those instantaneous values and you are deriving this particular case. What if your input is less than Vk? If your input is less than Vk, which is the dominating source, obviously Vk. So you can just write Vk dominates. Okay. If Vk dominates, then let us see what will happen to the circuit operation. So if Vk dominates, then Vk, as you can clearly observe that Vk is dominating in nature. And how Vk is being connected? The positive terminal of Vk is connected to diode. So Vk keeps the diode reverse bias in mode. Keeps the diode in reverse bias. So diode is treated as an open circuit element. Okay, and the resulting circuit takes the following shape. And this is your diode. So diode is behaving like an open circuit source or open circuit element because Vk is keeping the diode in reverse biasing mode. This is Vk. So the output we know. So in order to find the output, you can apply KVL, okay, in the clockwise direction. Though current is 0, still you will be having two potentials, input voltage and the output voltage. So you can apply KVL in the clockwise direction. So apply KVL. CWD stands for clockwise direction. So you have -2 plus Vi. Then current across Rs is 0 because I is 0 due to the open circuit nature of the circuit. And then you have plus to minus. So that is minus V0 is equal to 0. This implies that your output voltage V0 is equal to Vi. And what is Vi? Vi is positive half cycle. So during this instant when your input is less than Vk, you will get output is equal to Vi. So which is nothing but positive half. Fine. So case A is being dealt with. Now let us look at case B. What will happen when your input starts to dominate the barrier potential Vk? So when the input Vi starts to dominate Vk, that means to say, what if the potential of Vi is greater than Vk? So when Vi is greater than Vk, obviously Vi dominates. Okay, and let us comment on its dominance with the help of the circuit diagram. So this is your ideal diode, followed by alright. So which is the dominating source? Vi is the dominating source in this case. So as you can see that when Vi is dominating, the Vi is trying to circulate the current. In that process, the source Vi is going to forward bias the diode, right? Because anode is connected to the positive terminal of Vi. And Vi has come into existence because Vi is greater than Vk. So in this case, you can say that Vi biases, and therefore diode behaves like a closed. So let us redraw the circuit to support this particular case. So the diode acts like a closed switch, so we are going to replace the diode with a short circuit and a battery in place. Right. So this battery Vk models the barrier potential phenomenon. Alright, so you can observe the output. You don't have to apply KVL, though there is a closed circuit. Why, I'll tell you. So where are we observing the output? You are observing the output across, say, node A and say node B, correct? So output is observed across node A and B. And what do you have between node A and B? Between node A and B, you have a battery, right? So positive terminal of the battery is connected to node A and negative terminal of the battery is connected to node B. And you see the V0 sense. So V0 is measured between node A and B. So your output voltage V0 in this case is nothing but potential that exists between node A and B, which is Vk. So your output is basically a DC value. So what is the difference between ideal diode and practical diode analysis? In case of ideal diode analysis, you had obtained for the positive half cycle output V0 is equal to 0 volt. On the other hand, in case of practical diode analysis, you will get output is equal to 0 volt only when input is less than Vk. On the other hand, when your input is greater than Vk, output is not 0 volt. Instead, output is Vk. That means to say for a silicon diode, you may get the output which is in the range of 0.6 volts to 0.7 volts. And for a germanium diode, you may get the output in the range of 0.2 volts to 0.3 volts. So now let us look at the negative half cycle. So there won't be any changes in the negative half cycle. So let's flip the polarity. Diode symbol, barrier potential. Okay. Alright, so for the negative half cycle, you can see that both sources are trying to circulate the current in the same direction, right? Minus to plus, anti-clockwise direction. Minus to plus, anti-clockwise direction. So both the sources, you can say that they are helping each other in reverse biasing the diode. So for the entire negative half cycle, the diode stays in reverse biasing mode. So you can say that during negative half cycle, Vi and Vk keeps the diode in off state or reverse biasing state. So when the diode is not operating, you can replace diode with an open circuit. So diode can be treated open switch. Okay. So yeah, open switch as in so over here itself I have done the modification. So what I have done, I have removed the diode. On what basis I have removed the diode? Because diode needs to be treated as an open switch. So we have opened the diode terminals. So you can apply KVL. So, by observation, you can say that whatever input you give, that itself will come as the output. Okay. So apply KVL. Okay. In anti-clockwise direction. Okay. ACWD, anti-clockwise direction. So minus to plus Vi, then minus to plus V naught is equal to 0, or output voltage V naught is equal to minus Vi. Just like your ideal diode analysis. Even in case of ideal diode analysis, for the negative half cycle, you have obtained V naught is equal to minus Vi. So this negative sign simply indicates that output is an inverted waveform, which is nothing but negative half cycle of the. Alright, so now let us draw the waveform. So you have to recall the effect of Vk over here. So the barrier potential Vk, which was affecting which half cycle? The positive half cycle. So what you do is you draw Vk in the positive half cycle. So here you can write this is Vk level. So when you draw this Vk, that is nothing but the DC line, this Vk will give you a pair of intersection point with the positive half cycle. Okay, draw the projection line towards output time axis. Okay. Alright, so now let us investigate the circuit scenario. So during the time interval when your input voltage is less than the barrier potential Vk, we had obtained output is equal to input. Done. On the other hand, when your input voltage starts to exceed the Vk level, that means to say for any value of Vi greater than Vk, you had obtained output is equal to Vk. Once again, when the input falls below Vk level, that is in this region, your output becomes input. Right? So this is your positive half cycle, and you can see some flat line over here, right? So that flat line corresponds to Vk level. So this voltage value, if you read, you will get it as Vk. So in case of practical diode analysis, what you have to understand is that the positive half cycle is not completely clipped at 0 volt level. Instead, it is clipped at what voltage? 0.7 Vk, which is equal to 0.7 for silicon diode. Okay, so this is how the practical diode analysis differ from ideal analysis. Okay. On the other hand, for the negative half cycle, your output was minus Vi. That means to say your output is nothing but replica of the input. So input is negative half cycle. So for the entire negative half cycle, you will get a sinusoidal signal in the negative direction. Alright. And finally, let us draw the transfer characteristics for quadrant. Positive half cycle of the input, negative half cycle of the input, positive output, negative half cycle of the output. So during positive half cycle, there are two types of voltage levels. You have a flat line which corresponds to DC level, and you have a sinusoidal part which corresponds to AC level. So this is for positive half cycle. And for the negative half cycle, you have only one waveform, which is AC in nature. So in the previous class, as I mentioned, that whenever you have a DC signal, you're going to have a line parallel to x-axis in your transfer characteristics. On the other hand, whenever you have an AC signal, you're going to have an inclined line with an angle of 45 degrees. Alright, so we'll have to mark the threshold level, which is Vk. So this is the maximum value of the input. Let us mark it as Vm. and this is the threshold level Vk. And in your output also Vk level is present, that's why towards plus V0 you have to mark Vk as well. Alright. So as long as your input is less than Vk, what is the output? Output is Vi. So as long as your input is less than Vk, output is Vi. So Vi is AC, so straight line with a slope of 1. Okay. And inclination angle is 45 degrees. Okay. On the other hand, the moment the input starts to exceed Vk value, the output is going to get clipped at Vk level. So Vk level is nothing but your DC level. So you are going to have a flat line. Okay. So this is your DC signal. Okay. So as you can clearly observe in your transfer characteristics that you have AC signal as well as you have DC signal. Alright. And now let us visit the negative half cycle. So in the negative half cycle you can clearly observe that for the entire negative half cycle the output is the negative half cycle of the input itself. So this is minus Vm and this is minus Vm. Okay, so for the entire negative half cycle, the output is equal to minus Vi, which is nothing but unity slope with 45 degrees, drawn at an angle of 45 degrees. Okay, so that concludes today's session. Thank you.